try. We can see something. Now it will be perfect if you will press Ctrl plus
Yeah, I am trying again to do this. Is it okay now?
Yeah, it's excellent.
Okay, so you, first of all, good evening, good day, and good morning. So I hope that in this situation, this is just the right expressions. So you see that the title of my talk is Branching Process in Random Environment with Immigration Stopped at Zero. And in writing this talk, not in preparing, in a sense, this talk, you see that a huge team participated in. So from Russia, Charlene Smadi, she's formerly from Stiklo, but you know that this is because of the Russian Science Foundation requirements. She's from France. And then for the two nice girls from Beijing Normal University. So the topic will be branching process with immigration. And similar to Kostya's talk, there is some biological, in my case, biological motivation as well. So related with this problem. In fact, this is just related with evolution of populations and with extinction and appear in some genes and something like this. During my talk, I will show this. So let us recall you what is the Galton-Watson standard Galton-Watson process with immigration. So we have immigration. So initially we have some, this is a branching process. Initially we have some random number of individuals. Maybe it will be 0, maybe it will be 1, maybe it will be some random variable. And the distribution of the number of individuals in the moment n plus 1 is just sum of children of these guys which presented in the population moment n, plus some immigration, which is also depends on n. In this case, for ordinary Galton-Watson process with immigration, the number of children have the same distribution for all generations. The same is the number of immigrants is the same also for all generations. And the process is specified by two probability generating functions. F of s, this is the number of children of the aboriginal generation, so no immigrant, which describes the number of children of the basic particles of the process, and G of s, this is just the probability generating function for the number of children which comes to the respective generation. And of course, in the case of a Galton-Watson process in the random environment, in this case, probability generating function of the number of children are varying from generation to generation. And here, this is just the notation. So Fn of s, this is the number of children. Psi of n, this is the number of children of the n of particles of the n generation. And this is the distribution of the number of immigrants. And since we have a random environment, so it is assumed that this probability generating function are random and independent and identically distributed. And in this situation, again, branching process in random environment with immigration is specified by the same formulas. But the difference is that, first of all, that this number of individuals produced by the respective particles, they are now IID, but first of all, they depend on n. And also the number of immigrants is also IID, but it depends also on n. However, given that we know that the realization of the environment, because this sequence of F0, F1, and so on, G1 and G2 and so on, this is just is called a random environment. So in our case, I will consider another modification. I will consider branching process in a random environment with immigration, which is stopped at 0. What does it mean? Assume without loss of generality that we have initially positive number of individuals in the population. And then I define the process which is specified as follows. First of all, we allow to all the individuals of the previous generation, for instance, if this is generation 0, to produce children. And if the number of children which is produced by these initial individuals is equal to 0, so all the particles became childless, then we stop the process. Otherwise, we allow for immigration, and then we add to this process individuals which are immigrants. And so we continue this process, continue this process, and then we stop this process while these events happens. So this is the branching process with immigration stopped at 0, and the quantity zeta is called a life period of branching process with immigration stopped at 0. So this means that we have investigate, for instance, if some biological population comes to some group of animals comes to some place, so the other animals of the same type will join the population until this place will be empty. When this place will be empty, so the newcomers will come and new process biological start there, and so on and so on. For those who like queuing systems, the life period is closely related with the number of customers which will be solved during a busy period of some queuing system. So because there is a well-known connection between branching process and queuing systems, and so in these terms, in a sense, this quantity is related to the number of customers solved during the busy period of some server. So this is the definition of the process stopped at 0, and I will continue to. And the first part of my talk is just devoted to studying this process. So you know that there are two possibilities to study a branching process in a random environment. First of all, quench approach, so the study of the behavior of characteristic of branching process in random environment for typical realization of the environment, because the realization is random, and for this realization we study this quantity. And for instance, we would like to study the tail distribution of this life period. But in this case, of course, since this function f and g environment is random, so this quantity also will be random. So this will be random variables of the space of realization of the environment. This will be quench approach. And anneal approach, this is the study of the behavior of characteristic of a branching process, performing averaging over all possible scenarios on the space of realization of the environment. So we consider all possible scenarios. There is some probability measure on these scenarios, and then we take expectations to calculate this probability, for instance, to have a life period greater than t, and then we make averaging. And so in this case, this will be a number. And in this case, it is this case we would like to study in my talk. We would like to talk. So the aim of the talk is to present the results on the tail distribution of the random variable zeta under the annealed approach for branching processing with immigration stopped at 0. I would like to mention that Dubkov in 1972 investigated the distribution of life periods for ordinary Galton-Watson process with immigration. Later on, I will speak about this in more detail. So first of all, I would like to recall classification of Galton-Watson process in IID random environment. So in this classification, is based on the properties of the moment generating function. We take simply the derivative of this probability generating function, take log, take expectation, and this is just will be moment generating function which is of interest for us. And then classification of this branching process in random environment is the following. The process called supercritical if this expectation is positive, critical if this expectation is equal to 0, and subcritical if this expectation is less than 0. Better to see these by pictures, so this is just classification. So if we have this moment generating function, so in this case, the process is in random environment is called supercritical if this moment generating function derivative is here positive or equal to 0 or is negative, and so this is just splits the total amount of branching process with migration into three big classes. Of course, this is not all classes for branching process and random environment, but we concentrate only on these cases. So I will first of all mention the result about the critical case. So this is expectation log f prime equal to 0. So I will consider only fraction linear generating function. So geometric distribution. The geometric distribution is the reason for consider this class of process is twofold. Because first of all, it's possible to get explicitly formulas for probabilities of the length of this life period. This is one point. But the other point that it's really difficult to get rid of this condition. So this is an open problem in a sense, because we were trying to get rid of these conditions of this fraction linear case, but we failed to do this. And also there is a hypothesis which I would like to clarify a little bit. So first of all, f of 0 should be there should exist some constant kappa where f of 0 more than kappa should be with probability 1. This is what it is, because f of 0, this is just probability to produce children, to produce no children. And if this probability is equal to 0, of course, in this case, life period will be infinite for sure, because if you have such a possibility. So this is just to exclude this case where life period may be infinite. In this case, to study tail distribution is a stupidity. And then this estimate is of another kind, because g of s should be less than s to do some power gamma. If we again take now g equal to 1, so g equal to 1, sorry, if we take g equal to 1, this means that we should avoid the cases when there is no immigration. So in this case, there will be just another case, another process. So this is just the situation where we would like to get rid of the situation where there will be no immigration. And then this is technical condition. Forget about this. So this if all these conditions, technical conditions, are satisfied, then there exists a constant c positive side, that probability that the length of the life period will be more than n is just proportional to c divided by square root of n. And this is in fact, I will not show, of course, you proofs of this result, but the point is that this is just similar for ordinary branching process, for ordinary random walk to stay for a long time positive, because all these arguments which are used in branching process in a random environment, they are just based on the reduction of problems for branching process with immigration to problems related with random walk condition to stay positive, or condition to stay negative, or condition to just to reach the point 0 for the first time just at a fixed moment. So this results, if one has a desire to look for the proof, so he will see, or she will see for sure, that this is just results which relates life periods of branching process with immigration in random environment, just to studying ordinary random walk with to stay positive or to stay negative. I would like simply to compare this result with the results of Zubkov, which for ordinary critical Galton-Watson process, where he used these parameters. So this is now not random variable, because the ordinary Galton-Watson branching process is considered. And then Zubkov proved that in this case, life period behaves like this, where L of n is a slowly varying function as n tends to infinity. If this parameter theta is less than or equal to 1, and then it is proportional to some constant, so probability that our life period will be equal to infinity if this process is, if this parameter theta is more than 1. In the case of branching process in the random environment, because of fluctuations, this phenomena will never happen. There are, of course, other situations. So the subcritical case. In this case, the situation is more involved, because subcritical case, if we have subcritical case, then it happened that for branching process in random environment, also the behavior of the moment generating function at moment 1 is also of importance. And depending on the sign of the derivative, we will have absolutely different phenomena for this case. So this process is called strongly subcritical if this derivative is less than zero derivative of the moment generating function at moment 1. This process is called intermediate subcritical if this derivative is equal to 0. And finally, this process is called weakly subcritical if there is some point beta between 0 and 1, strictly less than 1, where this derivative is equal to 0. And depending on this process, we will have different behavior. I simply list these results, and it will be sufficient to understand those. So this is again a repetition of classification. So we have 3 main subclasses: strongly subcritical, that derivative is less than 0; intermediate subcritical is that this is equal to 0; and weakly subcritical if this parameter is equal to 0, and for some parameter beta. How to study this process? As usually it is done for ordinary random walks, it is necessary when for instance, people study large deviation, it is necessary to make a change of measure. And this change of measure is similar to change of measure, which is done usually for ordinary random walk. So in this case, we also make change of measure, but this change of measure is more complicated. You see that this change of measure, first of all, involves this probability generating function, and then also the values of our branching process with the migration stopped at 0. And this is this change of measure. So there is some initial measure, and for any bounded measurable function psi, we make this change of measure by this quantity gamma of n. And those who studied in Novosibirsk, I'm sure that they know how to change measure if you would like to study large deviations for ordinary random walk. And this is just the same change of measure, but the point is that here it is necessary to struggle with some additional randomness, because this kind of randomness, it is necessary to involve. And so in this case again, if we have, for instance, this quantity, so where delta is equal to 1 if we have intermediate or strongly subcritical process, or delta is equal to beta, which is between 0 and 1. Then in this case, under the new measure, this quantity x, which will generate some random walk, this quantity x will be driftless, and this helps a lot. And then if we make this change of measure and then make some tricks, then we are able to get some to prove some limit theorem, and this is some conditions. The point is that now we assume that the distribution of x is non-lattice and under new measure belongs to the domain of attraction of a two-sided stable law of index alpha. And and this is just allow us to attract results about random walk, for instance, standard random walk with tails which belongs to the domain of attraction of two-sided stable law. Of course, it is necessary to impose some restriction on the reproduction law of individuals under new measure. This is again, this condition exclude very, very reproductive particles, because this is the second derivatives in second moment, and this and the relations between second moment ratio to the square of the first moment of the number of particles. And of course, it is necessary to impose some conditions on the immigration components. This condition also excludes very, very productive particles. And these conditions, 1 minus g of 0 should be less than infinity. So it should, g of 0 should not be close to 1, because g of 0, this is just the number of individuals. The case when there is no immigration, and we would like to have immigration. And so if g of 0 is close to 1, this means that rather often we have no immigration, and we do not wish to consider such process, since we would like to consider branching process with immigration. And so if we have these conditions, then there is three types of behavior. First of all, the tail may be exponential or geometrical decay. The tail may have exponential decay or geometrical decay with time. Then even more rapid than geometrical with this parameter gamma, where this parameter gamma, recall you, this is the parameter gamma which we use to change the measure. And then there is only one non-trivial things in comparison with ordinary Galton-Watson branching processes. This is the influence on the environment, where we have this parameter alpha, which it includes stable distribution. So here we will have this gamma to the power n, and then divided by n to the power 1 plus 1 divided by alpha. This phenomena has no analogs for ordinary life periods of branching process with immigration. So this is the first part of my talk. The second part of my talk, which will be shorter, this is simply branching process in a random environment, survival of a single family only. And this is the following. Now we consider the situation where our branching process with immigration is very simple. So we add each time we add only single immigrant. But in order to study survival of a family, we would like to modify a little bit the process of appearance immigrants. So assume first that we have some, at moment n-1, we have some positive number of individuals in the population. Then we allow first again to produce children, but by all these individuals. And only afterwards, when we see the situation, we add exactly one immigrants to the population. So in this case, we are able to introduce the notion of survival of a single family only. How we will do this? First of all, we introduce the following definition. All individuals of the nth generation, which are children of the immigrant, which join the population at moment I less than n, they constitute the GN clan. So you may assume that for instance, this in the population will come, for instance, now COVID is everywhere, so some individuals, some immigrants which has some virus. So you may consider that, and then all these children will be those who were infected by him, and then by his children, by his grandchildren, and so on and so on and so on. But by the grandchildren, I consider that this is individuals which were infected by the previous generation, and so on and so on. And we say that only IN clan survives in this process to moment n if just children of this individual, if we consider all these individuals, which children of all individuals of n-1st generation, and all particles of this among this amount belongs just to the IN clan. And let ING be the event that only this IN clan survives in this process to moment n. And we study the asymptotic behavior of the probability of this event as n tends to infinity, and I varies with n in an appropriate way. This is why I split it in the process of immigration from the process of generating particles, because otherwise always there will be, if we allow immigration at the same time as the reproduction of individuals, so there will be always some other individuals in the population which do not belong to some particular clan, So now the results about again this is hypothesis that the random probability generating function is geometric with probability 1. This is because this again allow to calculate everything explicitly. This is the process critical. This is the critical case, and the distribution is absolutely continuous. And then after there is 3 types of behavior. If we consider individuals which enter the population, immigrants which enter the population just at the initial moment for a fixed moment I, then the probability that this clan will survive is proportional to n to 3 over 2, 1 over n 3 over 2. Then for any fixed n, if we, for instance, consider now the right side, so now we would like to consider what is the probability of survival only this clan, where clan was initiated just at the close to the moment of observation. Then this is power to n 1 over 2. And if in addition hypothesis 3 is valid, then which is here the distribution of x is absolutely continuous, then this limit as minimum gn n minus a tends to infinity, then this probability of this event will be just 1 divided by I to the power to the square root of I and square root of n minus I to the power of 3 over 2. So there is a smooth transition from n 3 over 2 to n to the power 1/2. But this smooth transition is rather strange, because it happens that if immigrants come to in the middle, so in this case they should survive with much smaller probability than these two. This is strange. For instance, if I is equal to n over half, n over to a half of n, then this will be just n to the power 2. So probability of this event will be 1 divided by n to the square, which seems strange, because but the reason is that here there will be 2 phenomena which will be glued together. So they should those who to the left should also die out, and those who will enter the population afterwards, all these clans also should die out. So this will be a combination of this situation. So this is also, there is a subcritical case, and again it's necessary in this case to make a change of measure again, and this may if we make a change of measure, we again will come to the situation where we should study large deviation of ordinary branch of ordinary random walk. And in this case, again, we are able to consider different conditions where, for instance, probability that our random walk will stay positive at some distant moment, and this new parameter rho will play the role, not only stable distribution, but also parameter rho. And in this case, for different situations, we will have different conclusions. But it seems to me that my time is over. So in this case, thank you for your attention.